There is a man in Sugar Creek, Ohio, who has not had a gas bill over $31 in January since 1986. He is not connected to a special utility program. He does not own solar panels. He has not installed a heat pump or a geothermal unit that cost $40,000 and required a licensed contractor and 3 permits and a check you had to write before winter came. He dug a trench by hand over 3 weekends with a shovel he already owned because he did not want to pay for a rental machine. He was 43 years old, and he was tired of writing checks to a gas company every January that felt like they were punishing him for living somewhere cold. That first winter, his bill dropped from $96 a month to $31. He thought it was a fluke, anomalous weather, a meter error, something. Because nothing that simple could produce a result that dramatic. So he tracked it. He kept paper records for 3 more years. The number held. It went down, actually. He added a second pipe in 1994 when he expanded his house. Today, in nominal dollars, before adjusting for the inflation that has quietly doubled and tripled the cost of everything else in your life, his January gas bill is lower than it was when Ronald Reagan was in the White House. The ground did that. Not a furnace upgrade. Not a government rebate. Not a contractor with a sales pitch and a financing plan. The ground beneath his yard, which had been sitting there at 55 degrees every January of every year he had ever lived in that house, did that. This is a story about something the earth has been offering you for free every winter for as long as you have owned your home. It is also a story about why you never heard about it. Those 2 stories are connected. They are connected by money, by legislation, by an industry that identified your ignorance as a revenue stream and spent decades and considerable political capital making sure that ignorance was protected. But we are going to start with the physics, because the physics is where the anger comes from. And the anger, once you understand what was withheld and why, is entirely justified. 4 feet below the surface of the earth, something remarkable happens. The chaos of the seasons, the brutal cold of a Minnesota February, the furnace heat of an August afternoon in Missouri, the wild swings of temperature that define life on the surface, none of it penetrates. The soil at 4 feet acts as one of the most effective thermal insulators in nature. It absorbs energy slowly, it releases energy slowly, and in the northern half of the United States, at that depth, the ground temperature stays in a remarkably narrow band, between 50 and 58 degrees Fahrenheit. Every month, every season, every year. This is not a theory. It is not a projection or a model or an estimate. It has been measured continuously across thousands of monitoring points in the United States and documented in academic, agricultural, and government literature going back well over a century. The ground at 4 feet does not care that it is January. It does not respond to the polar vortex. It holds its temperature with a consistency that no mechanical heating system in existence can match, because it is not mechanical. It is geological. It operates on timescales and energy budgets that dwarf anything human engineering has ever produced. Now think about what that means when you are trying to heat a house. On a January morning in Cleveland, the air temperature outside might be 8 degrees Fahrenheit. Your furnace, doing exactly what it was designed to do, pulls that 8-degree air in and has to close a gap of 62 degrees to bring the interior of your home to 70. Every single BTU of energy required to close that 62-degree gap costs you money. It costs you the money you paid for the gas or the electricity. It costs you the wear on the equipment. It costs you, over a 30-year mortgage, somewhere between $27,000 and $36,000 in heating bills paid to a single industry for a problem that the ground beneath your yard was already positioned to solve. Here is what the man in Sugar Creek understood, and what the Amish farmers of Holmes County and Lancaster County had understood for generations before him. You do not have to let that 8-degree air walk directly into your furnace. You can intercept it first. You can run it through a pipe buried at 4 feet, where the Earth sits at 55 degrees, and let the laws of thermodynamics do what they always do. Heat moves from warmer material to cooler material. That is not a theory or a principle or a guideline. It is a law. The same law that makes your coffee go cold and your ice melt. When 8-degree air moves through a pipe surrounded by 55-degree Earth, the Earth warms the air. By the time that air travels 40 feet through that pipe, it arrives at your furnace somewhere between 45 and 52 degrees. Your furnace now closes a gap of 18 to 25 degrees instead of 62. The documented reduction in heating load from a properly installed earth tube system in a climate like Cleveland or Pittsburgh is approximately 57%. In colder climates, Minnesota, Wisconsin, the Upper Peninsula of Michigan, where outside temperatures regularly drop below zero, the passive thermal gain is even more dramatic because the differential between the incoming air and the ground is wider. A research center in Ontario, Canada, the Courtright Center for Conservation, installed 9 earth tubes, each 20 meters long, buried at roughly 2 meters of depth. They measured every relevant variable through a complete winter cycle. Outside air entered the system at negative 12 degrees Celsius. It exited at positive 8 degrees Celsius. 20 degrees of passive thermal warming. No electricity consumed by the heating component. No combustion. No monthly bill attached to that 20 degrees of warmth. The physics has been documented. The results have been replicated. The technique has been in continuous use in parts of North America for over 200 years, and your gas bill has never reflected any of that. That is not an accident, it is a decision. And the people who made that decision and the legislative infrastructure they built to protect it are what this documentary is actually about. To understand how a 200-year-old technique that works, costs almost nothing to install, requires no ongoing payments, and has been validated by government research, university field studies, and the lived experience of thousands of households across the northern United States, simply vanished from every mainstream building guide written after 1960. You have to understand something about how industries protect themselves. Not from competition in the marketplace, where better products win and consumers benefit from the contest, but from the far more dangerous threat of irrelevance. The threat of a solution so simple and so permanent that no industry, no matter how well-funded or politically connected, can compete with it on merit. The natural gas industry in the United States is one of the most capital-intensive enterprises in the history of human civilization. The pipeline infrastructure alone, the network of transmission lines, distribution mains, service connections, metering equipment, and pressure regulation systems that delivers gas to approximately 74 million American homes and businesses represents a fixed investment measured in the hundreds of billions of dollars. That infrastructure does not generate returns unless gas flows through it. It does not pay for itself unless you use it. And every BTU of heat that your home captures passively from the earth beneath your yard is a BTU that does not flow through that pipeline, does not turn a meter, and does not appear as revenue on a quarterly earnings statement. This is the economic context you need to hold in your mind as we go forward. Because the suppression of passive heating technology was not driven by malice in the simple, dramatic sense. It was not a room full of villains deciding to harm ordinary people for sport. It was something more mundane and in many ways more troubling. It was an industry doing the rational thing, protecting its revenue, using its political access, its regulatory influence, and its financial resources to ensure that the alternatives to its product remained invisible, uncoded, unpermitted, and professionally untouchable. The mechanism through which this was accomplished is important to understand, because it is still operating right now, today, in state legislatures across the country. Building codes in the United States are not written by the government. Most people do not know this. The International Residential Code, which governs the construction of single-family homes and small residential buildings across the vast majority of American jurisdictions, is developed and maintained by the International Code Council, a private nonprofit organization. The membership of that organization includes representation from the construction industry, the materials industry, the equipment manufacturing industry, and the utilities. The code development process is open in the technical sense that anyone can submit a proposal, but navigating that process requires resources, expertise, legal support, and sustained organizational engagement that individual homeowners, independent researchers, and small advocacy groups simply do not have. The gas industry has all of those things in abundance. It has had them for 70 years. When natural gas infrastructure expanded across the American Midwest in the late 1950s and through the 1960s, reaching small towns and rural communities that had previously depended on wood, coal, and passive systems for heat, the building codes were rewritten to accommodate and encourage gas infrastructure. Gas furnaces became the default assumption embedded in residential construction standards. Duct sizing, air return specifications, combustion air requirements, ventilation calculations, all of it was written around gas heat as the baseline condition. Passive preheating systems, which required no utility connection and generated no ongoing revenue for any industry stakeholder, had no advocate in that process. They were not actively removed from the codes. They were simply never included. And once they were absent, their absence became self-reinforcing. A contractor who wants to build or install something in a permitted jurisdiction needs a code category to work within. No category means no approved pathway. No approved pathway means no permit. No permit means no contractor willing to accept the liability. No contractor means no installation. And no installation means the technology exists only in the hands of people willing to work outside the permitted system. People like the Amish, who operate under their own community standards, and individual homeowners willing to do the work themselves, quietly, without asking for official approval. This is how you bury a technology without burning a single document. You do not need to erase it from history. You simply need to ensure it has no place in the official present. The 1947 USDA Farmers Bulletin, document number 1918, titled Ventilation of Farm Buildings, contains a detailed section on underground air inlets. It describes pipe diameter, burial depth, length requirements, intake placement, and performance expectations. Written in plain language, published by the United States Department of Agriculture, validated by the Agricultural Research Network of its era, and made available for public use. That document did not disappear. It is sitting in the National Agricultural Library archives right now. It has been there continuously since 1947. It is publicly accessible, but it was never cited in the building guides that were written to replace it. It was never referenced in the residential construction standards that emerged in the post-war era. It was never incorporated into the training curricula of the professional associations that certify the contractors who build and renovate American homes. It simply stopped being mentioned. And in a world where professional practice is defined by what is mentioned in the official guides, a technology that is not mentioned does not exist in any practical sense. John Barnard understood this dynamic, though perhaps not in those exact terms, when he conducted his field study in the Rio Grande Valley in the winter of 1979. Barnard was working through the New Mexico Solar Energy Institute, an organization that received federal funding during the Carter administration as part of a broader national push toward energy independence following the oil shocks of the 1970s. That political moment, the brief window between 1977 and 1981, when the federal government was actively investing in alternatives to fossil fuel dependence, produced a remarkable body of research that has been almost entirely forgotten. Barnard's report, published in February 1980, under the title Passive Thermal Conditioning in Residential Construction, Field Measurements and Design Parameters, studied 12 homes that had installed what he called subterranean air tempering channels. His findings were significant not just for confirming the performance of Earth tube systems, which the Courtright Center would verify independently decades later, but for documenting something that had not previously been captured in the technical literature. These systems improve over time. The surrounding soil, which begins at its natural average temperature when the system is first installed, slowly adjusts to the air moving through the pipe across heating seasons. The ground immediately surrounding the tube warms slightly on average through the first and second winters because the air exiting the system carries slightly more thermal energy than the soil it started with. By the third winter, the surrounding Earth reaches a stable equilibrium with the system and performance plateaus at a level 8 to 12% more efficient than first-year operation. The system does not degrade, it does not wear out, it does not require maintenance contracts or replacement components. It improves, stabilizes, and then holds that performance indefinitely. Barnard's funding was eliminated in 1981, his report was filed, and for 40 years, it sat in the New Mexico State University Library archive, correct and ignored, waiting to be found by someone who knew to look for it. There is a particular kind of frustration that comes from learning that something simple and effective and essentially free was available to you the entire time you were paying for the expensive alternative. It is not the frustration of a complicated problem that resisted solution. It is the frustration of a simple solution that was kept just out of reach. The man in Sugar Creek, Ohio, found that solution because he was stubborn and skeptical and willing to dig. Most people never found it because the systems that were supposed to connect people with useful knowledge, the building industry, the contractor network, the code infrastructure, the utility companies themselves had every financial incentive to ensure the connection was never made. But before we go further into the architecture of suppression, we need to spend more time with the technology itself. Because part of what makes this story so remarkable is not just that Earth tube systems work, but how elegantly they work, and how thoroughly the physics behind them has been understood and documented across cultures and centuries with a consistency that should, by any reasonable standard, have made them impossible to ignore. The principle is ancient. It predates the Roman Empire, though the Romans applied it with characteristic engineering thoroughness. Archaeological evidence from sites across the Mediterranean basin shows the deliberate use of underground channels to moderate the temperature of air entering structures. In Persia, a sophisticated system called the Qanat combined underground water channels with ventilation towers to cool buildings in a desert climate where surface temperatures could exceed 50 degrees Celsius. The Qanat system was not a primitive experiment. It was a mature engineering tradition, refined across centuries, capable of cooling large structures to comfortable temperatures using nothing but the thermal mass of the Earth and the movement of air driven by differential pressure. Versions of it are still in use in Iran today. The same principle migrated westward and northward with the movement of agricultural civilization. In the Rhine Valley of what is now Germany, farmers building permanent structures in a climate with significant winter heating demands discovered the inverse application. The same Earth that could cool a building in summer could pre-warm the air entering it in winter. In 1897, a German architect named Heinrich Scholer published a technical paper documenting what he called the Erd-Keller the Earth Channel. Scholer was not proposing something new. He was documenting something that had been in continuous use in farmhouses across the region for at least 2 generations before him. His contribution was to apply the analytical framework of 19th century engineering science to a folk practice, measuring the temperatures, calculating the heat transfer coefficients, establishing the relationship between tube length and thermal gain that passive house researchers would independently rederive 100 years later. The physics Scholer documented in 1897 is identical to what the Courtright Center measured in Ontario in the early 2000s. It is identical to what John Barnard measured in New Mexico in 1979. It is identical to what the man in Sugar Creek, Ohio, experienced in 1986 when his January gas bill dropped by 2/3. The consistency across time, geography, research methodology, and cultural context is not coincidental. It reflects the fact that these measurements are all capturing the same underlying physical reality, which does not change because the political environment changes or because a particular industry finds the results inconvenient. Soil thermal mass is one of the most stable and predictable phenomena in applied physics. The specific heat capacity of soil, the amount of energy required to raise 1 kilogram of soil by 1 degree Celsius, is well established. The thermal diffusivity of soil, the rate at which temperature changes at the surface propagate downward, is well understood and has been measured extensively across different soil compositions. The combined effect of these properties is a phenomenon called thermal lag. The deeper you go below the surface, the more slowly the soil temperature responds to changes at the surface, and the smaller the amplitude of those changes becomes. At 1 foot of depth, the soil temperature follows the surface temperature with a lag of roughly a few days and an amplitude reduction of perhaps 20 to 30%. At 2 feet, the lag extends to weeks and the amplitude drops further. At 4 feet, the minimum recommended depth for an earth tube system, the seasonal temperature variation has been almost entirely damped out. What remains is a temperature that reflects the annual average air temperature of the region, modified slightly by the insulating properties of snow cover and vegetation. In northern Ohio, that temperature is approximately 54 to 56 degrees Fahrenheit. In Minnesota, it is slightly lower, around 48 to 52 degrees. In the mid-Atlantic states, slightly higher, but in every case, the ground at 4 feet is dramatically warmer than the winter air above it, and it maintains that temperature with a consistency that no mechanical system can replicate at any price. Now consider the economics of this with the precision they deserve, because vague claims about savings are not useful. Specific numbers, derived from documented installations and verified performance data, are what allow you to make an informed decision. The average American household in the northern states, let us define that as the band from Pennsylvania and Ohio westward through Indiana, Illinois, and Iowa, up through Wisconsin and Minnesota, spends between $900 and $1,200 per year on natural gas heating. That is the current average, reflecting gas prices that have been volatile over the past several years and remain subject to market forces entirely outside the homeowner's control. Over a 30-year mortgage, at the low end of that range and assuming no price increases, that is $27,000 paid to a gas utility for winter heat. At the high end, with the modest price increases that historical data suggest are essentially inevitable, the number climbs past $40,000. The installation cost of a basic earth tube system on an existing home is under $300 in materials. A rented walk-behind trencher costs approximately $150 to $200 per day and can cut a trench 4 feet deep through an average suburban yard in approximately 2 hours. 40 feet of 8-inch smooth bore PVC pipe costs between $60 and $90. A screened intake cap costs $12 at any hardware store. An inline duct fan capable of maintaining continuous slow airflow costs between $40 and $70 and consumes roughly the same electricity as a single incandescent light bulb. The total materials cost, including the drain fitting that proper installation requires, is under $350. The rental cost adds another $200 if you choose to use a machine rather than a shovel. A $500 investment producing a documented 50 to 78% reduction in heating load pays for itself in a single winter in most northern climates. In the second winter, it is generating pure savings. In the third winter, as Barnard's research documented, it is performing slightly better than it did in the first. In the 30th winter, it is still in the ground, still working, still warm. There is no financial instrument available to ordinary Americans that produces a return profile like that. There is no home improvement investment with a payback period measured in months and a performance horizon measured in decades with zero ongoing costs. The numbers are not complicated. They are almost insultingly straightforward once you see them laid out, which raises again the question that honest analysis cannot avoid. Why did it take this long to see them? The answer to that question does not begin in a boardroom or a legislative chamber, though it passes through both of those places on its way to your gas bill. It begins with something more fundamental: the relationship between knowledge and infrastructure, and the way that relationship was deliberately reshaped in the post-war American economy to serve the interests of industries that had made enormous capital commitments and needed guaranteed returns to justify them. In 1945, the United States emerged from the Second World War with an industrial capacity that had no peacetime precedent. The factories that had produced tanks and aircraft and ships were retooled for consumer goods. The engineers who had designed military infrastructure turned their attention to civilian construction, and the federal government, shaped by the experience of the New Deal and the wartime command economy, was prepared to invest massively in the physical infrastructure that would define American life for the next half-century. Roads, bridges, housing, and pipelines. The natural gas pipeline network that exists today was not built by market forces alone. It was built with federal support, federal right-of-way authority, federal regulatory frameworks that guaranteed returns to investors, and federal policy decisions that made natural gas the preferred fuel for residential heating in the post-war era. The interstate pipeline system expanded from roughly 150,000 miles in 1945 to over 300,000 miles by 1960. The distribution networks that fed gas from those transmission lines into individual homes and businesses grew at a corresponding rate. By the early 1960s, natural gas had displaced coal as the dominant residential heating fuel in most of the United States, not because it was necessarily the best available option for every household, but because it was the option that an enormous and politically connected infrastructure investment had been built to deliver. This is the context in which the underground air inlet disappeared from American building practice. It did not disappear because it stopped working. The physics did not change. The thermal mass of the Earth did not diminish. The 55-degree ground temperature that had been pre-warming farmhouse air in Lancaster County for 150 years was still there, still reliable, still free. But the economic and regulatory environment surrounding residential construction had been comprehensively restructured around a different model. A model in which heat was something you purchased from a utility, delivered through infrastructure you did not own, metered and billed on a monthly cycle that generated predictable, recurring revenue for an industry that had invested hundreds of billions of dollars in the expectation of exactly that revenue stream. Against that backdrop, the underground air inlet was not just inconvenient. It was structurally incompatible. A technology that requires no utility connection, no ongoing payments, no service contracts, and no professional installation infrastructure does not fit into an economy organized around the sale of energy as a commodity. It has no place in the supply chain. It generates no downstream revenue. It creates no customer relationship that can be monetized. It is, from the perspective of the energy industry, a dead end, not because it fails, but precisely because it succeeds, permanently, without further investment or involvement from any commercial entity. Understanding this helps explain something that otherwise seems almost inexplicable: why the professional construction industry, which is not owned by the gas companies and has no direct financial stake in gas utility revenues, also failed to adopt and promote earth tube technology. The answer is that the construction industry's professional infrastructure, its licensing bodies, its training programs, its liability insurance frameworks, its code compliance systems, was all organized around the technologies that the building codes recognized. A contractor trained in gas furnace installation, working in a jurisdiction where earth tube systems have no code category, operating under a liability insurance policy that covers approved installations and excludes unapproved ones, has every professional incentive to recommend the gas furnace and no professional pathway to recommend the earth tube, regardless of what the comparative economics suggest. This is how a technological suppression operates at scale without requiring explicit coordination or conspiracy. You do not need to instruct every contractor in America to avoid earth tubes. You simply need to ensure that the professional and regulatory environment makes the approved option the path of least resistance and the alternative option professionally and legally problematic. The individual contractor is not making an ideological choice. They are making a rational professional choice within a system that was designed to produce exactly that choice. The American Gas Association understood this dynamic with considerable sophistication. Founded in 1918, the AGA has spent over a century developing expertise in exactly this kind of systemic influence. It does not, for the most part, engage in the crude forms of industry advocacy that occasionally attract public attention and congressional scrutiny. It works at the level of standards, codes, training programs, and regulatory frameworks, the technical infrastructure that shapes professional practice in ways that are largely invisible to the public and largely impenetrable to outsiders without the resources and expertise to engage with them on their own terms. The AGA's annual budget runs into the tens of millions of dollars. Its membership includes the major natural gas utilities, the pipeline operators, and the equipment manufacturers whose products depend on gas infrastructure remaining dominant. Its Washington office maintains relationships with every relevant regulatory agency and congressional committee. Its technical staff participates in the code development processes that determine what gets built in American homes and what does not. And embedded in your monthly gas bill, in a line item that most customers have never examined closely, is a small contribution to the AGA's operations and lobbying activities that is a condition of your service agreement, not a voluntary choice. 70 million American households pay that contribution every month. Most of them have no idea they are doing it. Most of them would be surprised to learn that a portion of what they pay, their gas utility, flows to an organization whose explicit mission includes protecting the market position of natural gas against alternatives, including the passive thermal alternatives that the earth beneath their yards was already providing for free. In March of 2020, the American Gas Association held an internal planning meeting that would, through a series of investigative reports over the following years, become one of the more illuminating documents in the history of American energy politics. The minutes from that meeting described heating alternatives, not just heat pumps and solar thermal systems, but the entire category of passive and reduced consumption approaches as what the AGA called an existential threat to natural gas direct use in buildings. That language is precise and revealing. Not a competitive challenge, not a market pressure, an existential threat. The kind of threat that justifies extraordinary responses. The response the AGA chose was not to compete. It was not to invest in research that might demonstrate the superior economics of gas heat against passive alternatives. It was to legislate, to use the political access that decades of lobbying investment had purchased to push through state-level preemption laws that would block local governments from encouraging or requiring the kinds of building practices that might reduce gas consumption. Since 2020, versions of that legislation have passed in more than 25 states. The bills were not written by the state legislators who introduced them. When researchers ran the text of multiple state versions through plagiarism detection software, the results were striking. The language, structure, and specific provisions were nearly identical across states as geographically and politically diverse as Utah, Texas, Arizona, and Louisiana, appearing in state houses within months of each other. A Utah state representative, asked directly where his version of the bill came from, did not claim to have written it. He said he had become aware of it from his local gas supplier. A utility company wrote a state law. A state representative introduced it. And 70 million households now have fewer options because of it. To truly grasp the scale of what was lost, when passive thermal technology was systematically excluded from American building practice, you need to travel to a place where it was never lost. A place where the economic logic of dependency was evaluated and rejected, not in a laboratory or a legislative chamber, but in the quiet deliberations of a community that understood, with a clarity that modern consumer culture rarely achieves, the difference between a tool and a leash. Holmes County, Ohio, sits in the rolling hill country of the northeastern part of the state, about 60 miles south of Cleveland and 40 miles west of the Pennsylvania border. It is the heart of the largest Amish settlement in the world, a community of roughly 40,000 people living according to principles of faith, community, and intentional simplicity that have remained largely consistent since their ancestors arrived in Pennsylvania from German-speaking Europe in the early 1700s. The farmhouses of Holmes County are not museums. They are working structures, housing working families, managing real agricultural operations in a climate that delivers genuine winter cold every year without apology. And some of them, the older ones, the ones that have been continuously maintained and inhabited across multiple generations, are still using earth-air systems that their builders installed over a century ago. Not as historical curiosities, not as demonstrations of heritage, as functional components of how the house manages temperature and air quality, integrated into the building's design as naturally and practically as the roof or the foundation walls. The first time a researcher or a journalist walks into one of these homes expecting to find the dry, slightly stale, forced air heat that has become the default sensory experience of American interior winter, what they find instead is something qualitatively different. The warmth is even. It does not cycle on and off with the compressor rhythm that furnace heat produces. The air has a quality that is difficult to describe precisely but immediately noticeable, slightly humid, fresh, without the faint smell of combustion that even the most efficient gas furnace introduces. It feels less like a heated space and more like a naturally temperate one. This is not aesthetics. It reflects a genuine physical difference in how the heat is being delivered. A gas furnace heats air to temperatures well above the desired room temperature and then circulates it rapidly, producing temperature gradients within the room, cycling the humidity down with each pass through the heat exchanger, and introducing the minor combustion byproducts that modern high-efficiency units minimize but cannot entirely eliminate. An earth tube system delivers air that has been gently pre-warmed by thermal exchange with the surrounding soil air that arrives at something close to the desired temperature, carrying the natural humidity and atmospheric composition of outdoor air, requiring only a small additional boost from a secondary heat source to reach full comfort temperature. The Amish did not develop this preference through academic analysis of HVAC engineering. They developed it through generations of lived experience in buildings that worked this way, combined with a community framework that evaluated technology not on the basis of novelty or convenience, but on the basis of what the Amish call Gelassenheit, a concept that translates roughly as yielding or submission to the community and to God, but which in practical terms functions as a systematic evaluation of whether a technology increases or decreases dependency, whether it strengthens or weakens the community's capacity for self-sufficiency. An earth tube fails every test that makes the Amish community skeptical of technology in the way that most outsiders misunderstand that skepticism. It does not create dependency on a corporation. It does not require a monthly payment. It cannot be cut off for non-payment or adjusted in price by a supplier responding to market conditions. It does not require specialized knowledge to maintain, because it requires essentially no maintenance at all. Once it is installed correctly, with proper slope and drainage as the critical technical requirements, it functions indefinitely. The clay pipe systems that some Lancaster County farmhouses still show evidence of, systems installed in the early 1800s, were still delivering pre-warmed air to those houses when their owners were great-grandparents. The technology predates the American gas industry by a century. It will likely outlast it. This is the specific quality that makes earth tube systems so threatening to an industry built on recurring revenue. They are permanent solutions. They do not need to be replaced. They do not need to be upgraded. They do not create an ongoing customer relationship that can be monetized. In the economics of the modern utility industry, a customer who has installed an earth tube system is a customer whose heating load has been permanently and irreversibly reduced. That reduction does not expire. It does not require renewal. It compounds slightly over the first 3 years as the surrounding soil reaches thermal equilibrium with the system, and then it holds at that improved level for as long as the pipe remains in the ground. For the gas industry, the actuarial mathematics of this are straightforward and alarming. A homeowner who installs a basic earth tube system at age 40 and lives in the house until age 70 has reduced their gas consumption by 50 to 78% for 30 consecutive heating seasons. At current gas prices, that represents somewhere between $15,000 and $25,000 in revenue that will never flow through the pipeline. Multiplied across the 74 million American households currently connected to natural gas infrastructure, the revenue implications of widespread earth tube adoption are not merely significant, they are existential in precisely the way the AGA's internal planning document described. This is why the suppression of this technology was not a casual or incidental outcome of the gas industry's political activities. It was and remains a strategic priority. The legislative effort to preempt local building codes, the systematic exclusion of passive thermal systems from the International Residential Code, the absence of earth tube training from every major contractor certification program in the country, these are not coincidences or oversights. They are the predictable outputs of a sustained, well-funded, strategically sophisticated campaign to ensure that the technology the Amish have been using since their great-grandparents built the first farmhouses in Holmes County never becomes standard practice in the communities outside the fence line of Amish settlement. But here is the thing about a technology this simple, this well-documented, and this economically compelling: it does not require institutional support to survive. It does not need a trade association, or a code category, or a contractor certification program. It needs a trench, some pipe, and someone willing to dig. The man in Sugar Creek dug his trench with a shovel in 1986 because he did not want to pay for a rental machine. He did not have a government grant, or a contractor's license, or a building permit. He had a shovel, a weekend, and the stubborn conviction that there had to be a better answer than writing a check to the gas company every January for the rest of his life. He was right. And the document that confirmed he was right had been sitting in the National Agricultural Library since 1947, published by his own government, available to anyone who knew to look for it. The question is not whether the technology works. That question was settled 200 years ago in the farmhouses of the Rhine Valley, confirmed 100 years ago by Heinrich Schöller's careful measurements, validated again in 1947 by the USDA, again in 1980 by John Barnard, again in the early 2000s by the Courtright Center, and demonstrated continuously across every winter that has passed in Holmes County since the first German-speaking settlers arrived with their knowledge and their clay pipes and their deep suspicion of dependency. The question is what you are going to do with that knowledge now that you have it. Before we talk about what you can do with this knowledge, we need to talk about what happened to the people who tried to make this knowledge mainstream. Because the story of earth tube suppression is not just a story about a technology that was quietly excluded from building codes and professional practice. It is a story about researchers whose funding was eliminated, institutions whose mandates were defunded, and a brief window of political will in the late 1970s that was systematically closed before it could produce lasting change. To understand that window, you need to understand the energy crisis of the 1970s with a precision that popular memory rarely supplies. The oil embargo of 1973, triggered by the OPEC nations' response to American support for Israel during the Yom Kippur War, produced a shock to the American economy that went far deeper than the gasoline lines and the odd-even rationing that most people remember from that period. It revealed, with a clarity that was genuinely alarming to policymakers at the highest levels, the degree to which the American economy had been built on an assumption of cheap and abundant fossil energy that was not guaranteed to remain true. The vulnerability was not merely inconvenient, it was strategic. An economy that could be brought to its knees by a foreign cartel's decision to restrict oil exports was an economy with a fundamental security problem. The policy response to that recognition, under both the Nixon and Ford administrations, but most aggressively under Jimmy Carter, was a serious and sustained investment in energy alternatives, not as an environmental gesture or a political signal, but as a genuine national security imperative. The Department of Energy was created in 1977. The Solar Energy Research Institute, later renamed the National Renewable Energy Laboratory, was established in Golden, Colorado. Regional research centers focused on passive solar, earth thermal, wind, and biomass energy were funded across the country. The New Mexico Solar Energy Institute, through which John Barnard conducted his field study of subterranean air tempering channels, was one of dozens of such organizations that received federal support during this period. The research produced during this window was extraordinary in its breadth and practical applicability. Passive solar design principles, earth thermal systems, super insulation techniques, thermal mass construction. The body of knowledge developed between 1975 and 1981 represented a genuine technological foundation for a residential construction industry that could have dramatically reduced American dependence on fossil fuel heating. Many of the techniques documented during this period required no exotic materials, no complex engineering, and no ongoing utility connection. They were, like the earth tube system, things that could be built by an informed homeowner with basic tools and a modest materials budget. In January of 1981, Ronald Reagan took office. Within weeks, the funding landscape for alternative energy research changed with a speed and completeness that researchers who had been working in the field still describe with a kind of stunned disbelief decades later. The Solar Energy Research Institute had its budget cut by approximately 90%. Regional research centers were closed. The passive solar and earth thermal research programs that had been building toward practical construction guidelines and code adoption were defunded before their work could be institutionalized. John Barnard's report on subterranean air tempering channels, published just 1 year before the funding was eliminated, never received the follow-up research and code development work that would have been required to move it from an academic finding into standard building practice. The Reagan administration's energy policy was not secret or subtle about its priorities. The solar panels that Jimmy Carter had installed on the White House roof as a symbolic gesture toward energy independence were removed. The tax credits for renewable energy and passive thermal installations that had begun to create market incentives for alternative systems were allowed to expire. The message to the construction industry, the building codes community, and the research establishment was unambiguous. The era of federally supported alternative energy development was over, and the future belonged to fossil fuels. What made this policy shift so consequential for the specific technology we are discussing was not just the defunding of research, it was the timing. Earth tube systems, passive solar design, and the other techniques developed during the Carter-era research push were at precisely the stage where sustained institutional support would have moved them from promising findings into mainstream practice. The research had been done, the performance had been documented, the cost-effectiveness had been demonstrated. What remained was the translation work. Getting these techniques into the building codes, into contractor training programs, into the professional literature that shapes what gets built. That translation work requires sustained funding, sustained institutional presence, and sustained political support. All three were eliminated simultaneously in 1981. The gas industry did not need to do anything active at that moment. The political environment had done the work for them. The research programs were closed. The researchers moved on to other projects. The reports sat in university archives, correct and ignored. And the building codes continued to evolve without any of the passive thermal provisions that might have entered them if the research programs had continued for another 5 years. This is the historical mechanism through which the knowledge gap was created and maintained. It was not a single dramatic act of suppression. It was a sequence of policy decisions, each individually explicable on its own terms, that collectively produced an outcome that served the gas industry's interests with remarkable precision. The defunding of alternative energy research in 1981. The absence of passive thermal categories in the International Residential Code. The preemption legislation that the AGA has been pushing through state legislatures since 2020. These are not independent events. They are chapters in a continuous story about who controls the infrastructure of knowledge and how that control translates into recurring revenue extracted from households that were never given the information they needed to make a different choice. But there is a parallel story running alongside the institutional one, and it is in some ways more important. Because while the research programs were being defunded and the building codes were being written to exclude passive thermal systems, the knowledge itself was not destroyed. It was preserved in exactly the places where no industry pressure and no policy decision could reach it. In the farmhouses of Holmes County, in the archives of the National Agricultural Library, in the footnotes of passive house technical papers written by European researchers whose funding environments were different, in the memory of men like the one in Sugar Creek, Ohio, who dug a trench with a shovel and tracked his gas bill for 40 years because he wanted to understand what he had found. Knowledge that is true does not require institutional support to remain true. It requires only that someone, somewhere, continues to practice it and remember it and pass it on. The Amish provided that continuity for earth tube technology in America for the entire period between the post-war expansion of gas infrastructure and the present moment. They did not do it as an act of preservation or resistance. They did it because the systems worked, and because in a community that evaluates technology on the basis of practical effectiveness and freedom from dependency, working systems that create no dependency are simply kept. The clay pipe systems in Lancaster County farmhouses are not relics. They are working embodiments of a principle that the gas industry spent decades and considerable political capital trying to make invisible. The principle is simple. The earth beneath your feet is a thermal resource of extraordinary stability and availability. It does not meter itself. It does not send invoices. It does not lobby state legislatures or fund preemption campaigns. It simply holds its temperature 4 feet down, 55 degrees, every January, every February, every year you have lived in your house. And it will be there next winter too. Whether or not a contractor is willing to install it, whether or not your state's building code has a category for it, whether or not the gas company would prefer you not to know about it, the trench does not care about any of that. Let us talk about the practical reality of building one of these systems, because theory without implementation is just another document sitting in an archive. The gap between understanding that earth tube systems work and actually having one in the ground beneath your yard is a gap that can be closed in a single weekend by a person of ordinary physical capability with no specialized knowledge and no professional credentials. But closing that gap requires specific information, not vague encouragement. And the specific information is where most of the guides and videos and articles that touch on this subject fall short. The first decision you need to make is about location, and it is more consequential than most guides acknowledge. The ideal routing for an earth tube system on an existing home runs from an intake point at the far end of your property, or at least as far from the house as your yard permits, in a straight line or gentle curve toward the home's existing air return system. Straight runs are preferable to curved ones because curves create turbulence that slightly reduces airflow efficiency and, more importantly, create low points where condensate can collect if the slope calculation is not precise. If your yard geometry requires a curved run, the curve should be gradual and the slope must be verified along the entire length of the run, not just at the endpoints. The intake point location matters for 2 reasons. First, you want the intake as far from the house as practical to maximize the length of pipe in contact with thermally stable soil, away from the thermal influence of the building's foundation, which modifies ground temperature in the immediate vicinity of the structure. Second, you want the intake positioned away from any source of contaminated air. This means maintaining distance from septic systems, from areas where vehicles are regularly operated, from compost piles, and from any other potential source of biological or chemical contamination. A minimum distance of 20 feet from a septic system is the conservative standard. 30 feet is better. The intake should also be positioned away from areas of standing water or poor drainage, which can introduce moisture into the system at a rate that exceeds the drainage capacity. The depth question deserves more nuance than the standard 4-foot recommendation conveys. 4 feet is the minimum depth at which seasonal temperature variation is sufficiently damped to provide reliable thermal performance across the full heating season. But in the coldest climates, the northern tier of states where January temperatures regularly drop below 0 Fahrenheit, there is a measurable performance benefit to going deeper. At 5 feet, the ground temperature in Minnesota or Wisconsin is marginally more stable and marginally warmer in the coldest months than at 4 feet, because you are further from the surface influence and deeper into the zone of annual average temperature equilibrium. The difference is not dramatic, perhaps 2 to 3 degrees Fahrenheit of additional pre-warming, but in a climate where your starting point is -20 and every degree matters, that additional depth is worth the extra time on the trencher. The trenching itself, which is the part of the project that intimidates most people before they actually do it, is straightforward with the right equipment. A walk-behind trencher, available at virtually every equipment rental outlet in the country for approximately $150 to $200 per day, can cut a trench 4 to 5 feet deep through average residential soil in approximately 2 hours for a 40-foot run. The trench width needs to accommodate the pipe diameter with enough clearance for proper bedding material on all sides. For an 8-inch pipe, a 12-inch trench width is adequate. For a 10-inch pipe, which is worth considering in colder climates where higher air volume increases thermal exchange efficiency, 14 inches is the comfortable working width. The pipe specification is where a significant number of do-it-yourself installations make their first and most consequential error. The recommendation for smoothbore PVC is not arbitrary. It is based on the aerodynamic and hygienic characteristics of the pipe interior. Corrugated pipe, which is cheaper and easier to work with in some respects, has a dramatically higher surface roughness that creates turbulence in the airflow, reduces the efficiency of the inline fan, and critically provides hundreds of small valleys and ridges where condensate can collect and where biological material can accumulate. The mold concern that critics of earth tube systems most frequently raise is, in every documented case of actual mold development in these systems, traceable to the use of corrugated pipe or to improper slope that produce standing condensate. Smoothbore PVC with a properly maintained slope is categorically different in its hygiene performance from corrugated installations. The European Passive House Institute's 5-year microbiological monitoring of properly designed smoothbore systems found 0 measurable contamination. That finding does not extend to corrugated pipe installations, and the distinction matters enormously. The slope specification, 1 inch of drop per 10 feet of run toward the intake end, sounds simple and is simple in principle, but requires deliberate attention during installation because residential yards rarely have the perfectly even grade that makes slope verification straightforward. The correct procedure is to establish the slope using a transit level or a long level and story pole before the pipe is bedded, verify it at multiple points along the run, and make any necessary adjustments to the trench bottom before laying the pipe. Trying to verify and correct slope after the pipe is in place is significantly more difficult and produces less reliable results. The 10 minutes spent confirming slope before bedding the pipe is the most valuable 10 minutes in the entire installation. The bedding material beneath and around the pipe serves 2 purposes. It provides the stable, uniform support that prevents pipe movement and slope change after backfilling. And it provides the thermal contact between the pipe exterior and the surrounding soil that is the mechanism of heat transfer. Compacted native soil is adequate bedding in most conditions. In areas with rocky soil, where achieving uniform pipe contact without voids is difficult, a thin layer of clean sand as bedding material ensures complete contact and eliminates air gaps that would reduce thermal exchange efficiency. The connection point at the house is the element of the installation that benefits most from advanced planning and the element that is most specific to your home's existing HVAC configuration. For a home with forced air heating, the most common residential heating system in the United States, the connection into the cold air return is the path of least resistance and the highest performance integration. The cold air return is the duct that carries room temperature air back to the furnace for reheating. Introducing pre-warmed earth tube air at this point means your furnace is working with air that has already been elevated 40 to 50 degrees above outdoor temperature, which produces the dramatic reduction in heating load that the documented cases show. The integration requires cutting an opening in the cold air return duct, installing a properly sized transition fitting to match the earth tube pipe diameter to the duct dimensions, and installing a damper that allows you to control the proportion of earth tube air versus recirculated room air entering the furnace. The damper is not strictly necessary for the system to function, but it gives you operational flexibility, the ability to reduce earth tube airflow during the brief shoulder seasons when outdoor temperatures are mild and pre-warming is less beneficial, and to maximize it during the deep cold periods when the thermal benefit is greatest. For homes with baseboard, electric heat, or radiant systems where there is no forced air duct to connect into, the integration approach is different but not significantly more complex. In these homes, the earth tube functions as a dedicated fresh air preconditioning system, delivering pre-warmed outdoor air to a single well-positioned supply point in the home's interior. The air movement creates a gentle positive pressure that drives air circulation through the living space and out through natural leakage points in the building envelope. The heating load reduction is somewhat less dramatic than in a forced air integration because you are not directly reducing the inlet temperature of the primary heating system, but the fresh air quality benefit is significant and the thermal contribution is real and measurable. The inline duct fan that maintains airflow through the system is the only component that requires electricity, and its consumption is modest enough to be essentially negligible in the context of overall household energy use. A properly sized fan for a 40-foot, 8-inch tube draws between 30 and 60 watts, continuously less than a standard incandescent light bulb. At average residential electricity rates, the annual operating cost of the fan is between $20 and $50. Against a heating load reduction of several $100s per winter, the economics of the fan's electricity consumption are not a meaningful consideration. What is a meaningful consideration is fan placement and specification. The fan should be located at the house end of the system, pulling air through the tube rather than pushing it from the intake end. Pull configuration is preferable for two reasons. It keeps the fan in the conditioned space where it is accessible for maintenance, and it maintains the tube under slight negative pressure, which ensures that any minor leakage in the pipe connections draws in surrounding soil atmosphere rather than allowing conditioned house air to escape into the ground. These are the details that separate a system that performs reliably for 30 years from one that creates problems in the second winter. Not complicated details, not details that require professional expertise or specialized tools, details that require attention, precision, and the willingness to do the job correctly the first time rather than quickly. The man in Sugar Creek did it correctly the first time, with a shovel and a level, and 40 years of subsequent gas bills that proved it. There is a document that most people who know about earth tubes have never seen. Not because it is difficult to find, but because the chain of citations that would lead a curious person to it was severed before it could become established, and the researchers who would have built that chain had their funding eliminated before they could do the work. The document is John Barnard's 1980 Field Report, Passive Thermal Conditioning in Residential Construction, Field Measurements and Design Parameters, and it contains something that changes the economic calculation of earth tube installation in a way that no subsequent guide or video has adequately communicated. Barnard's finding about performance improvement over time is the piece of this story that deserves far more attention than it has received. The standard presentation of earth tube economics focuses on first-year performance. Install the system, reduce your heating load by 50 to 78%, calculate the payback period, conclude that the investment is sound. That presentation is accurate as far as it goes, but it understates the case because it treats the system's performance as static when Barnard's data shows it is dynamic and the direction of that dynamic is upward. To understand why earth tube systems improve over time, You need to think carefully about what is actually happening in the soil surrounding the pipe during the first several heating seasons. When the system is first installed, the soil at 4 feet is at its natural, undisturbed temperature, the annual average for that location, which reflects the long-term balance between surface heat input from solar radiation and heat loss from the ground surface through radiation, convection, and conduction. That temperature has been stable for a very long time, perhaps for the entire period since the last significant disturbance of the soil, whether agricultural or geological. When you begin running cold winter air through a pipe embedded in that soil, you are introducing a new energy exchange into that equilibrium. The air entering the pipe in January is significantly colder than the surrounding soil. The soil warms the air. In warming the air, the soil loses a small amount of thermal energy. That energy deficit in the soil immediately surrounding the pipe is replenished by conduction from the surrounding soil mass, which draws from the larger thermal reservoir of the earth at depth. But the replenishment is not instantaneous, and it is not perfectly efficient. Over the course of a heating season, the soil in the immediate vicinity of the pipe, within perhaps 6 to 12 inches of the pipe wall, experiences a slight net cooling effect as it gives up more thermal energy to the passing air than it receives back from the surrounding mass during that same period. This slight cooling of the immediately surrounding soil would seem to suggest that performance should decrease over time as the soil closest to the pipe becomes slightly cooler and therefore has less thermal energy to transfer to incoming air. But Barnard's measurements showed the opposite, and the reason is subtle and important. The cooling of the immediately surrounding soil increases the thermal gradient between that soil and the deeper, undisturbed earth. A steeper gradient drives faster conduction. Over the course of the first 2 to 3 heating seasons, this increased gradient actually accelerates the rate at which the deep Earth's thermal reservoir replenishes the soil around the pipe, and the system reaches a new equilibrium, one in which the pipe is surrounded by soil that is slightly better connected, thermally speaking, to the stable deep Earth reservoir than the undisturbed soil was before installation. The practical result, as Barnard measured across his 12 Rio Grande Valley installations, is a performance improvement of 8 to 12% between first year and third year operation, after which performance stabilizes at the improved level for a system that is already producing a 50 to 78% reduction in heating load in its first year. An additional 8 to 12% improvement in year 3 is significant. It represents the difference between, say, a 60% first-year load reduction and a 67% third-year load reduction, numbers that compound significantly across the 30-year horizon of a mortgage. What Barnard also documented, and what has been confirmed by European passive house research conducted decades later, is the converse of this improvement dynamic. Earth tube systems do not degrade. The mechanisms of failure that affect mechanical heating systems, component wear, refrigerant loss, heat exchanger fouling, blower motor deterioration have no equivalent in a properly installed earth tube. The pipe does not wear. The soil does not deplete. The thermal mass of the earth is effectively infinite on the timescales relevant to residential construction. A properly installed smoothbore PVC system with correct slope and drainage has no theoretical service life limit. The practical limit is the service life of the pipe material itself, which for Schedule 40 PVC in a buried application is estimated by manufacturers at 100 years or more. The man in Sugar Creek installed his system in 1986. It has been running continuously for nearly 4 decades. He has not replaced any components. He has not had the pipe inspected or serviced. He added a second tube in 1994, which required the same installation process as the first, and both tubes have been running continuously since. His gas bill has not increased in nominal terms since 1986. It has decreased slightly, which is consistent with Barnard's finding that performance improves and stabilizes rather than declining. When asked about maintenance, he says, "There is nothing to maintain. The ground does not require maintenance." This permanent and improving performance profile has implications that extend beyond the individual household economics, though those are compelling enough on their own. It has implications for how we think about the relationship between residential infrastructure and energy markets, and about the degree to which the current structure of that relationship reflects genuine economic efficiency, or the legacy of political decisions made to protect a particular industry's revenue stream. Consider the aggregate numbers. The United States has approximately 74 million households connected to natural gas heating infrastructure. The average northern state household spends between $900 and $1,200 annually on gas heating. If every one of those households had installed a basic earth tube system at the time of the home's construction, using materials that cost less than $500 at any point in the last 50 years, the aggregate reduction in annual gas expenditure would be somewhere between $30 and $50 billion per year, depending on the assumed load reduction percentage and current gas prices. That $30 to $50 billion per year is money that currently flows from household budgets to gas utilities, pipeline operators, and the investors who own them. It is money that pays for the infrastructure that delivers gas to homes that could be heating themselves with a pipe and some soil. It is money that funds the lobbying operations that push preemption legislation through state houses. It is money that pays for the professional association staff who engage in the building code process to ensure that passive thermal systems remain without a code category. The circularity of this system is its most elegant and most troubling feature. Households pay gas bills fund utilities fund lobbying suppresses alternatives. Suppressed alternatives mean households continue paying gas bills. The cycle is self-reinforcing and self-funding, and it has been running continuously since the post-war expansion of gas infrastructure created the revenue base that made the lobbying investment worthwhile. Breaking that cycle does not require legislation or regulatory action or political will at the national level. It requires a shovel or a rental trencher and 40 feet of smooth-bore PVC pipe. It requires the specific knowledge that was documented in 1947, confirmed in 1980, verified in the early 2000s, and practiced continuously in Holmes County for over 200 years. It requires understanding that the system improves over time, that it requires no maintenance, that it has no theoretical service life limit, and that the 8 to 12% performance improvement Barnard documented means that every year you run the system, you are getting slightly more value from the same installation. It requires, most fundamentally, understanding that the gap between what you are paying and what you could be paying is not the result of the problem being difficult. It is the result of the solution being inconvenient for people whose business model depends on the problem continuing. The physics does not care about the business model. The soil at 4 feet does not consult a quarterly earnings statement before deciding what temperature to hold. The thermal laws that Schuler documented in 1897 and Barnard confirmed in 1980 and the Courtright Center verified in the 2000s are not subject to revision by the American Gas Association's legislative strategy team, regardless of how many state preemption bills they manage to pass. The earth beneath your yard is holding 55 degrees right now. It held that temperature last January while you wrote a check to the gas company. It will hold it next January. The only variable in that equation that can change is whether you have a pipe down there to capture what the earth has been offering you all along. The condensation question is the one that stops more people from completing an earth tube installation than any other technical concern, and it stops them not because the problem is unsolvable, but because the way the problem is typically presented makes it sound more complex and more threatening than it actually is. Critics of earth tube systems have used the condensation issue as their primary technical objection for decades, and in the specific context of poorly designed systems, they are entirely correct to do so. Condensation in an improperly installed earth tube is a real problem with real consequences. But the solution is so straightforward and so thoroughly documented by both engineering analysis and centuries of practical experience that the condensation objection functions less as a legitimate technical concern and more as a conversation stopper deployed to discourage investigation. Let us be precise about what condensation is and when it occurs, because precision is what separates a valid engineering concern from a vague deterrent. Condensation occurs when air containing water vapor contacts a surface that is at or below the dew point temperature of that air. The dew point is the temperature at which the air becomes saturated, unable to hold any more water vapor in gaseous form, and any further cooling causes that vapor to condense into liquid water on available surfaces. In the context of an earth tube system, the relevant scenario is this: warm, humid summer air entering the tube contacts the cooler pipe wall and condenses moisture on that surface. In winter operation, the scenario reverses: cold, dry incoming air is warmed by contact with the pipe wall, and the pipe wall itself remains above the dew point of the incoming air, which means condensation during winter heating operation is minimal to non-existent in most climates. The condensation concern is therefore primarily a summer phenomenon, which means it is most relevant to people who plan to run their earth tube system year-round, using it for both summer cooling and winter preheating. For winter-only operation in cold climates, condensation is rarely a significant issue because the incoming air in January is cold and dry, and the warming it receives from the pipe makes it less likely to reach saturation, not more. This distinction is important because most of the alarming accounts of mold in earth tube systems involve summer operation in humid climates, and those accounts are frequently cited as evidence against winter heating applications where the physics is fundamentally different. For year-round operation, which is the configuration that delivers the maximum economic benefit because it addresses both summer cooling and winter preheating with a single installation, the condensation management system is not optional. It is the difference between a system that performs reliably for decades and one that develops problems within a few seasons. But properly implemented, it is not complicated. The Amish farmers of Lancaster County figured it out with clay pipes and gravel beds in the early 1800s, and their solution was structurally identical to what modern passive house engineers specify today. The two requirements are non-negotiable and completely interdependent. First, the pipe must slope continuously and without interruption toward the outdoor intake end, at a minimum grade of 1 inch per 10 feet of run. This single requirement is the most important element of the entire condensation management system. A continuous downward slope toward the intake means that any condensate that forms on the pipe walls during summer operation runs toward the intake end under gravity rather than pooling at low points inside the system. Gravity is reliable in a way that no mechanical drainage system is. It does not require electricity. It does not require maintenance. It does not fail. A pipe with correct and continuous slope toward the intake will self-drain by gravity indefinitely. The second requirement follows directly from the first. If condensate is running toward the intake end, you need a drainage point at the intake end where that condensate can exit the system rather than accumulating. This is the drain trap that costs approximately $8 and installs in 10 minutes. A simple P-trap or condensate drain at the lowest point of the intake end allows water to exit while preventing air from bypassing the system. In the original Amish installations, the intake sat over a gravel bed that absorbed and dispersed the condensate naturally. The gravel bed is equally effective and arguably more elegant, requiring no maintenance and no components that can fail, at the cost of slightly more excavation at the intake end to prepare the gravel drainage bed. The European Passive House Institute's microbiological monitoring program, which tracked biological activity in properly designed earth tube systems over 5-year periods, found zero measurable contamination in systems that met these two specifications. Zero. Not minimal contamination, not manageable contamination. No measurable biological activity after 5 years of continuous operation in systems with correct slope and adequate drainage. The mold concern, which critics deploy as though it were an inherent and unavoidable characteristic of earth tube systems, is in fact a characteristic of specific design failures that are entirely preventable with basic attention to slope and drainage. The pipe material specification is the third element of condensation management. and it interacts with the slope and drainage requirements in ways that make substituting corrugated pipe for smooth-bore PVC a particularly consequential error. Corrugated pipe's interior surface is not a smooth, inclined plane down which condensate can flow freely. It is a series of ridges and valleys, each valley capable of holding a small pool of standing water regardless of the overall slope of the pipe run. Even with correct average slope, the individual corrugation valleys are level and will collect condensate. Over time, those collections become the biological substrate that critics correctly identify as problematic. Smooth bore pipe with correct slope has no such collection points. Condensate that forms on the pipe wall runs continuously toward the drain point without impediment. The pipe interior remains effectively dry between operating cycles. This is why the smooth bore specification is not a preference or a suggestion. It is the technical basis for the zero contamination finding. A corrugated pipe installation, regardless of how carefully the slope is maintained, cannot achieve the same result because the pipe geometry prevents it. The additional cost of smooth, bore-over corrugated pipe for a 40-foot installation is approximately $20 to $40. The performance and hygiene difference is not marginal, it is categorical. Understanding these three requirements, continuous slope, adequate drainage, smooth bore pipe, allows you to evaluate any earth tube installation you read about or encounter with appropriate precision. Systems that developed mold or biological contamination can almost always be traced to one or more of these three failures. Systems that have operated cleanly for 5, 10, 20, or in some Amish farmhouses 200 years consistently reflect all three. The Amish did not have polymer chemistry knowledge or passive house engineering standards when they laid those clay pipes in the early 1800s. But they had generations of accumulated practical knowledge about what happened when the pipes sloped incorrectly, and they built accordingly. There is one additional technical consideration that most guides address inadequately, and it concerns the relationship between earth tube airflow velocity and thermal exchange efficiency. The rate at which air moves through the tube affects how much thermal energy it absorbs from the surrounding soil, and the relationship is not linear. Very slow airflow maximizes the contact time between the air and the pipe wall, which maximizes thermal exchange but reduces the volume of pre-warmed air delivered to the house per unit time. Very fast airflow increases air volume but reduces contact time and therefore reduces the temperature gain per unit of air. The optimal airflow velocity for an 8-inch tube is between 1 and 2 meters per second, a rate that balances thermal exchange efficiency against air volume delivery and is well within the performance range of the standard inline duct fans recommended for these systems. The inline fan specification matters here. Underpowered fans that cannot maintain the target velocity reduce system performance during the periods of highest heating demand, which tend to be the coldest nights when wind resistance and density effects make moving air through the system slightly harder. Overpowered fans that move air too quickly sacrifice thermal exchange efficiency for volume. The sweet spot for a 40-foot, 8-inch system is a fan rated for approximately 200 to 250 cubic feet per minute at the static pressure created by the tube length and any transitions in the connection to the house ductwork. Fan specifications are available from manufacturers and are straightforward to match to system requirements once you have the tube dimensions. The complete technical picture is this: a properly specified system using smooth-bore PVC at the correct diameter, installed at 4 feet or deeper with continuous slope toward a drained intake, connected to an appropriately sized inline fan, integrated into the home's existing air return or fresh air supply, will perform, as documented, 50 to 78% heating load reduction in first-year operation, improving to 8 to 12% above that baseline by the third year, with zero maintenance requirements and no theoretical service life limit. That is what one weekend and under $500 in materials and rental equipment will buy you. That is what the man in Sugar Creek has had since 1986. That is what the Amish have had since their great-grandparents arrived from the Rhine Valley with clay pipes and the knowledge of how to use them. The only thing standing between that outcome and your January gas bill is the trench. There is a specific kind of courage required to act on knowledge that the official systems around you have conspired, whether through active suppression or structural neglect, to keep invisible. It is not the dramatic courage of public confrontation or political resistance. It is the quieter, more practical courage of deciding that your own direct experience of a verified physical reality outweighs the absence of official permission to act on it. The man in Sugar Creek had that courage in 1986. The Amish community of Holmes County has exercised it continuously for 2 centuries. John Barnard had it when he published his field report in 1980, knowing that the political environment was about to eliminate the institutional support that would have given his findings traction. Heinrich Scholler had it in 1897 when he committed to paper a careful, technical documentation of something that the engineering establishment of his era considered folk practice beneath serious analysis. What each of these people understood, in their different ways and different eras, is that the validation of a physical truth does not depend on institutional recognition. The Earth holds 55 degrees at 4 feet regardless of what the International Residential Code says about it. The thermal laws that govern heat transfer between moving air and surrounding soil do not consult the American Gas Association's legislative strategy before operating. The performance improvement that Barnard documented in his 12 Rio Grande Valley installations does not require a building permit to occur. Physical reality is indifferent to the political and economic structures that human beings build around it, and that indifference is, in the specific context of Earth tube systems, an extraordinarily powerful fact. It means that the suppression, however sustained and sophisticated, was never total. It could not be total because the knowledge it was suppressing was not abstract or theoretical or dependent on specialized equipment that could be controlled. It was knowledge about a property of the Earth itself, demonstrable by anyone with a thermometer and a shovel, verifiable by direct experience in the first winter of operation. You cannot regulate the thermal mass of soil. You cannot lobby the specific heat capacity of the Earth into irrelevance. You cannot write a preemption bill that prevents the ground at 4 feet from holding 55 degrees. This is why the story we have been telling across these parts is ultimately not a story of defeat, it is a story of delay. The gas industry, through its code influence and its legislative campaigns and its systematic exclusion of passive thermal systems from professional practice, managed to delay the widespread adoption of earth tube technology for approximately 60 years. 60 years of gas bills that did not need to be written at anything close to their actual amounts. 60 years of heating loads that the Earth was already positioned to dramatically reduce. 60 years of infrastructure investment justified by a demand that passive thermal systems would have significantly curtailed. That delay has been costly in human terms. The aggregate gas expenditure of American households over those 60 years, the portion of it that earth tube systems would have eliminated, represents a transfer of wealth from ordinary households to energy industry investors on a scale that is genuinely difficult to comprehend. But the delay is not permanent, and its end does not require a legislative victory or a code reform or a change in the professional culture of the construction industry. It requires exactly what the man in Sugar Creek required in 1986, the decision to dig. But making that decision well, in a way that produces the maximum benefit and avoids the specific failure modes that critics correctly identify in poorly executed installations, requires something beyond the basic physics and the basic installation specifications we have covered. It requires an honest accounting of the variables that affect system performance in your specific location, your specific home, and your specific heating situation. Because while the fundamental physics is universal, the practical outcomes vary with conditions, and understanding that variation is what allows you to set accurate expectations and make sound decisions. The most important location variable is the ground temperature at depth, which is a function of your regional climate expressed as an annual average. The United States Geological Survey maintains ground temperature monitoring data across the country, and the general pattern is well established. In the Deep South, ground temperature at 4 feet approaches 70 degrees Fahrenheit, which means earth tube systems provide minimal winter preheating benefit but significant summer cooling benefit. In the Mid-Atlantic and Ohio Valley regions, ground temperature runs between 54 and 58 degrees, providing strong winter performance. In the upper Midwest and northern tier states, ground temperature at 4 feet is typically between 48 and 54 degrees, slightly lower than the mid-continent average, but still dramatically warmer than the January air temperatures in those regions. The thermal benefit calculation for your specific location is the difference between your average January low temperature and the ground temperature at 4 feet in your area. In Minneapolis, where January lows average around 3 degrees Fahrenheit and ground temperature at 4 feet is approximately 50 degrees, the passive thermal gain from a properly installed earth tube is approximately 47 degrees Fahrenheit. Your furnace, which was previously closing a gap from 3 degrees to 70, now closes a gap from 50 degrees to 70. That is a reduction in heating load of approximately 73%. In Pittsburgh, where January lows average around 22 degrees and ground temperature runs around 55 degrees, the gain is 33 degrees, and the load reduction is approximately 60%. In Chicago, the numbers fall between those two examples. In every case, the reduction is substantial. In no northern climate is it negligible. The home variable that most significantly affects the practical impact of the load reduction is your home's existing insulation and air sealing quality. An earth tube system reduces the thermal load associated with heating incoming ventilation air. In a well-insulated, well-sealed home, ventilation air heating represents a relatively larger proportion of total heating load because conduction losses through walls and ceiling are minimized. In a poorly insulated home with significant conduction losses, ventilation heating is a smaller proportion of total load, and the earth tube's impact on total bills, while still meaningful, is proportionally smaller. This does not mean that poorly insulated homes should not install earth tube systems. It means they should install earth tube systems and also address their insulation deficiencies, because the two improvements are complementary and their benefits compound. A home that reduces ventilation heating load by 60% through an earth tube system and simultaneously reduces conduction losses by 30% through added insulation achieves a total heating reduction that is greater than the sum of the two individual improvements, because the reduced conduction losses mean the furnace runs less frequently to maintain set point, which means the improved ventilation air temperature has more opportunities to reduce startup heating demand. The interaction between earth tube performance and existing HVAC system efficiency is similarly important to understand. A high-efficiency condensing gas furnace operating at 95% efficiency extracts more usable heat from each unit of gas than an older 80% efficiency unit. But both furnaces are equally benefited by receiving pre-warmed air because the thermal load reduction applies to the input side of the efficiency calculation regardless of the output efficiency. A 95% efficient furnace receiving 50-degree air instead of 8-degree air uses the same proportion less gas as an 80% efficient furnace in the same situation. The earth tube's benefit is upstream of the furnace efficiency, which means it compounds with furnace efficiency improvements rather than competing with them. There is a practical question that comes up in almost every serious conversation about earth tube installation on existing homes, and it concerns the interaction between the earth tube fresh air supply and the home's existing ventilation and combustion air systems. Modern building codes require that gas appliances, furnaces, water heaters, fireplaces have adequate combustion air supply. In tightly built newer homes, this is typically addressed through dedicated combustion air intakes. In older homes, it has historically been addressed through building envelope leakage. When you add an earth tube system that introduces a controlled volume of fresh air into the home's air handling system, you are changing the home's air balance, and that change needs to be evaluated in the context of the combustion air requirements of the appliances in the home. In most existing homes with older, less efficient furnaces and significant envelope leakage, the additional fresh air introduced by the earth tube system does not create combustion air problems, it supplements an already generous supply. In newer, tighter homes with sealed combustion appliances that draw their combustion air directly from outside through dedicated pipes, the earth tube supply is separate from the combustion air system, and the interaction is minimal. The scenario that requires attention is a tight, newer home with an older atmospheric combustion furnace that draws combustion air from the indoor air supply. In that specific configuration, professional evaluation of the combustion air balance before and after earth tube installation is the conservative and correct approach. These variables and their interactions are not reasons to hesitate. They are reasons to be informed. The man in Sugar Creek did not have access to USGS ground temperature data or passive house engineering standards when he dug his trench in 1986. He had observation, common sense, and the practical knowledge that the Earth was warmer than the January air. That was enough to produce a system that has been running for nearly 4 decades without a single component replacement. You have access to everything he had, plus everything that has been documented, measured, and verified in the 40 years since. The knowledge is complete, the physics is settled, the economics are unambiguous. The installation is within the capability of any person willing to spend a weekend with a shovel or a rented trencher, and the specific attention to slope, drainage, and pipe specification that separates a 30-year system from a problematic one. The Earth is ready. It has been ready every January of every year you have owned your home. The only question that remains is whether you are ready to meet it halfway, 4 feet down, where the temperature holds and the bills stop. The geographic reach of this technology is broader than most people assume when they first encounter it, and the assumption that Earth tube systems are primarily relevant to the coldest northern climates is one that deserves direct correction. The physics of passive thermal exchange operates on a principle of differential. The greater the difference between the incoming air temperature and the ground temperature, the greater the thermal gain. This does make northern climates the most dramatic beneficiaries of winter preheating applications. But the same differential principle applies in the other direction during summer, and it applies with significant economic force in climates that experience hot summers even when their winters are mild. Understanding the full geographic range of Earth tube applicability is important because it expands the population of households for whom this technology represents a meaningful economic opportunity far beyond the Minnesota and Wisconsin households that the most dramatic case studies tend to feature. Consider the climate of the American Southeast. In Georgia, Alabama, Mississippi, and the Carolinas, winter heating loads are modest compared to the northern tier states. January lows in Atlanta average around 33 degrees Fahrenheit, and the heating season is short enough that winter preheating alone might not justify the installation cost in purely economic terms, though the math remains favorable even there. But summer cooling loads in those same states are substantial and sustained. Atlanta's July high average exceeds 88 degrees. The cooling season runs from May through September, 5 months of significant air conditioning demand. And at 4 feet below the Atlanta suburbs, the ground temperature holds at approximately 62 to 65 degrees Fahrenheit year-round, as it always has. The same pipe that pre-warms incoming air in a Minnesota January performs the opposite function in a Georgia July. Outdoor air entering the system at 90 degrees Fahrenheit contacts pipe walls surrounded by 63-degree earth. Heat transfers from the warmer air to the cooler soil. By the time the air exits the tube, it has been cooled to somewhere between 68 and 72 degrees, still not air-conditioned, but dramatically closer to comfort temperature than the 90-degree air that entered the system. Your air conditioner closes a gap from 70 degrees to 70 instead of from 90 degrees to 70. The cooling load reduction in properly documented southeastern installations runs between 40 and 60% during peak summer months. The economic significance of this in the southeast is considerable. The average Georgia or Alabama household spends between $800 and $1,100 annually on air conditioning. A 40 to 60% reduction in cooling load produces savings of $300 to $600 per summer against an installation cost that remains under $500. The payback period is less than 2 years in most southeastern applications. And unlike the winter application, where the earth tube is working hardest precisely when the heating demand is greatest, the summer cooling application benefits from a dynamic that makes it particularly effective during the periods of peak demand. The hottest days tend to have the highest outdoor temperatures, which means the differential between incoming air and ground temperature is greatest on the days when you most need the cooling benefit. This year-round applicability, winter preheating in the north, summer pre-cooling in the south, and both functions in the vast middle band of the country where both heating and cooling demands are significant, means that earth tube technology is not a regional solution. It is a national one, applicable in every climate zone of the continental United States with meaningful economic benefit in every one of them. The specific numbers vary by location, but the principle holds everywhere the ground exists at a stable temperature below the seasonal extremes of the surface. Which is to say, everywhere, the international evidence reinforces this geographic universality. In Central Europe, where the passive house movement has been most rigorously developed and most comprehensively documented, earth tube systems known in the German language technical literature as Erdwärmetauscher, or earth heat exchangers, have been installed in thousands of certified passive house buildings across a range of climates, from the relatively mild conditions of southern Germany and Austria to the more demanding winters of Scandinavia and the Alpine regions. The European Passive House Institute's database of monitored installations spans over 2 decades of continuous performance data, and the consistent finding across that entire database is that properly designed earth tube systems perform within the predicted range in every climate where they have been installed and monitored. The German and Austrian experience is particularly instructive because it developed in a regulatory environment that, unlike the American one, actually incorporated passive thermal systems into building standards rather than excluding them. The German Energy Saving Ordinance, known by its German acronym NEV, has included provisions for earth-coupled air preheating since the early 2000s. German architects and engineers are trained in the design and specification of these systems as a standard component of energy-efficient building practice. German contractors install them routinely. German building inspectors approve them without hesitation because the code provides a clear pathway and the performance standards are well established. The result is that in Germany, earth tube technology is not a hidden folk practice preserved by a minority community that operates outside the mainstream construction industry. It is a mainstream construction technique used in tens of thousands of buildings across the country. The contrast with the American situation could not be more stark. In Germany, a homeowner who wants to install an earth tube system calls a contractor, gets a quote, pulls a permit, and has a professionally installed and inspected system within a few weeks. In the United States, the same homeowner faces a code environment where the technology has no approved pathway, a contractor community where the liability exposure of installing unapproved systems deters professional engagement, and a regulatory environment that in more than 25 states has been actively shaped by legislation written by gas utility companies to protect their market position. The German experience also provides the longest continuous dataset for earth tube performance monitoring, and that dataset addresses one of the questions that long-term skeptics most frequently raise. What happens to these systems after 20 or 30 years of continuous operation? The answer, from the German Passive House Monitoring Database, is that nothing happens to them in the pejorative sense. They continue to perform. The smoothbore pipe does not corrode in normal soil conditions. The thermal exchange efficiency does not diminish. The slope does not change unless the soil around the pipe is disturbed by some external force. The inline fans, which are the only mechanical component in the system, require periodic replacement, typically every 10 to 15 years depending on operating hours and fan quality, but the fan replacement cost of $50 to $70 does not meaningfully affect the long-term economics of a system that is saving hundreds of dollars annually. The 20 to 30-year performance data from German installations also confirms Barnard's finding about the improvement dynamic in the early years of operation. Multiple monitored German installations show the same pattern: measurably improved performance in years 2 and 3 compared to year 1, followed by stable performance at the improved level for as long as monitoring has continued. The German data extends Barnard's 3-year observation window to 20 years in some cases, and the stability finding is unambiguous. These systems do not plateau and then begin declining. They plateau and hold, indefinitely, at the improved performance level established in the first 3 years of operation. The Chinese experience adds another dimension to the geographic universality argument. In the northern Chinese provinces of Heilongjiang, Jilin, and Inner Mongolia, where winters are severe by any standard, January temperatures in Harbin regularly reach -25 degrees Celsius. Earth-coupled ventilation systems have been incorporated into building design as part of China's massive investment in energy-efficient construction over the past 2 decades. The Chinese building standard GB 50176, the Thermal Design Code for Civil Buildings, includes provisions for earth-coupled air systems that reflect the accumulated international evidence on performance and design requirements. Chinese research institutions have published extensively on earth tube performance in extreme cold climates, and their findings consistently confirm the international pattern. Significant passive thermal gain, improvement in early years, long-term stability. The global convergence of this evidence, from German passive house databases to Chinese building standards to Canadian Research Center measurements to John Barnard's 1,980 field report sitting in a New Mexico University archive, is not coincidental. It reflects the fact that these researchers and institutions, working independently across decades and continents, are all measuring the same physical reality. The Earth holds its temperature at depth. Moving air through that depth captures thermal energy. The system improves slightly in the first 3 years and then holds its performance indefinitely. This is not a contested finding. It is not a finding that requires further study or additional verification. It is an established physical fact documented by independent researchers in multiple countries across multiple decades using multiple methodologies. The only place this established physical fact has been systematically absent from mainstream practice is the United States, where an industry with revenues to protect and political access to exercise made certain that the knowledge gap was maintained long enough for the infrastructure investment to pay for itself many times over. That strategy has been extraordinarily successful on its own terms. The gas industry's returns on its pipeline infrastructure investment have been substantial and sustained across the 60 years during which passive thermal technology was kept out of the mainstream. But strategies that depend on information asymmetry have a fundamental vulnerability. They collapse when the asymmetry is eliminated. And the asymmetry is being eliminated not through regulatory action or legislative victory, but through the accumulation of accessible information that makes the suppression increasingly difficult to maintain. The European Passive House literature is available online. The Courtright Center research is publicly accessible. John Barnard's 1,980 report is in a digital archive that anyone with an internet connection can reach. The USDA Farmers Bulletin number 1,918 is in the National Agricultural Library's digital collection. The physics is in every thermodynamics textbook ever written. The knowledge that the gas industry spent decades keeping invisible is now, for anyone willing to spend an afternoon reading, completely visible. The question is no longer whether you can find it. The question is what you choose to do with it. The human cost of this suppression is not adequately captured by aggregate economic statistics, as compelling as those numbers are. $30 to $50 billion in annual gas expenditure that passive thermal systems would have eliminated. $27,000 to $40,000 over a 30-year mortgage that the average northern state household paid to a gas utility for a problem the earth beneath their yard was already solving. These figures are real, and they are important, but they abstract the experience into numbers in a way that obscures what those numbers actually represent in the lives of ordinary people. What they represent is choices that were not available. The family in Cleveland that kept the thermostat at 62 degrees through January because the bill at 68 was something the budget could not absorb, The retired couple in Milwaukee who spent the last week of every February calculating whether the heating bill or the medication copay had more flexibility. The young family in Minneapolis buying their first house, looking at the January utility estimates and adjusting what they could afford to spend on the mortgage because the heating costs were fixed and non-negotiable and substantial. These are not marginal cases or extreme examples. They are the ordinary arithmetic of winter in the northern United States, experienced by tens of millions of households across every heating season of the past 60 years. And behind every one of those calculations, at 4 feet below the yard of every one of those houses, the ground was holding 55 degrees. The thermal resource that would have changed the arithmetic was there, available, free, and kept invisible by a combination of code exclusion, professional deterrence, legislative preemption, and the systematic defunding of the research programs that would have made it visible. The anger that this generates, when you understand it fully, is appropriate. It is not the anger of conspiracy thinking or grievance politics. It is the anger of a person who has been given an accurate accounting of something that was done to them and to their parents and to their grandparents by people and institutions who understood exactly what they were doing and why. The American Gas Association's internal planning document did not accidentally describe heating alternatives as an existential threat. It used that language deliberately because the people who wrote it understood that passive thermal systems, if widely adopted, would permanently and irreversibly reduce the revenue base that justified the infrastructure investment and the shareholder returns that depended on it. They understood the stakes. They responded accordingly. And the response worked for 60 years at a cost to ordinary American households that is measured in the hundreds of billions of dollars. But here is what the accounting also shows, when you extend it beyond the history of suppression and into the practical present. Every year that passes without an earth tube in the ground beneath your house is a year of gas bills that did not need to be written at their full amount. And every year that passes with an earth tube in the ground is a year of savings that compounds slightly as the system improves toward its third-year performance plateau. The suppression has already cost you whatever it has cost you across the years you have owned your home. That cost is sunk, it cannot be recovered. But the forward calculation is entirely different, and the forward calculation favors action with an urgency that the economics make unambiguous. A household in Cleveland that installs a basic earth tube system this spring will see its first full winter of reduced heating bills in the season beginning next October. The payback on the installation cost will be complete before the second winter ends. By the third winter, the system will be performing at its plateau efficiency, and every subsequent January will deliver savings that have no expiration date, no rate increase, and no legislative vulnerability. The gas company cannot raise the price of the Earth's thermal mass. The AGA cannot lobby the specific heat capacity of soil into obsolescence. The preemption legislation that is passed in 25 states cannot prevent the ground 4 feet below your yard from holding 55 degrees. This forward-looking calculation also needs to account for something that the standard economic presentations of earth tube systems rarely address with sufficient weight: the trajectory of natural gas prices. The assumption embedded in most savings calculations is that current gas prices represent a reasonable baseline for projecting future costs. That assumption has not been well supported by the historical record, and there are structural reasons to believe it will be even less well supported in the coming decades. Natural gas prices have been volatile throughout the period of gas infrastructure dominance. The price spikes of 2005 and 2008, the prolonged period of low prices enabled by the shale revolution between 2012 and 2020, and the dramatic price increases of 2021 and 2022 triggered by supply disruptions and demand surges collectively demonstrate that residential gas customers are exposed to commodity price risk that they have no individual ability to hedge. The 74 million American households connected to gas heating infrastructure are, in effect, holding an unhedged long position in natural gas futures every winter, and that position is managed not by professional risk analysts making decisions on their behalf, but by utility company procurement departments whose interests do not perfectly align with household budget stability. The structural outlook for gas prices adds additional pressure to this already unfavorable risk profile. The transition away from fossil fuels and electricity generation, however uneven and politically contested, is reducing the industrial and power generation demand that has historically stabilized gas markets. As large industrial and commercial consumers electrify, the residential customer base becomes a larger proportion of total gas system throughput, which means residential customers bear a larger share of the fixed infrastructure costs that must be recovered regardless of total volume. This dynamic, known in utility economics as the death spiral, has already been observed in the electric utility sector as rooftop solar adoption reduces grid throughput, and there is no structural reason it cannot repeat in the gas sector as heating alternatives reduce residential gas consumption. In plain terms, the real cost trajectory of gas heating over the next 30 years is almost certainly upward, and the factors driving that trajectory are structural rather than cyclical. A household that installs an earth tube system today is not just capturing current savings, it is hedging against a price risk that is real, substantial, and unlikely to resolve in the household's favor. The 55-degree ground temperature does not participate in commodity markets. It does not respond to supply disruptions in the Permian Basin or demand surges in export markets. It holds its temperature regardless of what natural gas trades at on the NYMEX. That price stability, which is absolute and permanent, has a value that the standard savings calculations do not fully capture. There is also a dimension of this story that extends beyond the individual household into the community and the culture, and it is a dimension that the Amish understanding of technology illuminates with particular clarity. The Amish evaluation of a technology asks not just whether it works, but what kind of relationship it creates. A technology that creates dependency on a corporation, on infrastructure you do not own, on a supply chain you cannot control, on a payment obligation that can be enforced against you, is evaluated with deep skepticism regardless of its performance characteristics. A technology that eliminates dependency, that performs its function without requiring ongoing external inputs, that cannot be turned off or made more expensive by a third party, that strengthens rather than weakens the household's capacity for self-sufficiency, is evaluated with corresponding favor. By that standard, an earth tube system is not just an economic improvement. It is a change in the fundamental character of the household's relationship to its heating infrastructure. A household with an earth tube system is not a customer in the same sense that a household without one is. Its heating load is substantially and permanently reduced. Its exposure to gas price volatility is dramatically decreased. Its dependence on the gas utility's continued willingness to supply at current prices is significantly diminished. It has, in the precise sense that the Amish use the word, reduced its dependency. That reduction has value that goes beyond the dollar savings. Though the dollar savings are substantial enough to justify the installation on purely financial grounds, it has the value of security. The security of knowing that your household's thermal comfort in January does not depend on a commodity market, a utility company's pricing decisions, or a legislative environment that an industry association's lobbyists are continuously working to shape in directions that serve the industry's interests rather than yours. The man in Sugar Creek understood this, not in the abstract language of energy economics or political analysis, but in the direct, practical language of a man who dug a trench and watched his January gas bill drop by 2/3 and never go back up. He did not frame it as resistance or as politics. He framed it the way Eli, the Amish farmer outside Millersburg, framed it when someone asked him about his heating system. The ground is the furnace, and the ground, unlike every other furnace available to the American homeowner, belongs to no one who can charge you for using it. We have spent considerable time building the case for why earth tube technology works, why it was suppressed, what the economics look like across different time frames and climate zones, and how the installation should be properly executed to produce reliable long-term performance. Now it is time to address something that the advocates of this technology including this documentary, have a responsibility to handle with complete honesty. The limitations, the legitimate caveats, and the scenarios where earth tube systems are not the right solution or not the complete solution, because a technology presented without its limitations is not being presented honestly. An honest presentation is the only kind that serves the people who need this information to make real decisions about real houses in real climates. The first and most important limitation is one that has been implicit throughout this documentary but deserves explicit statement. An earth tube system is not a heating system. It is a heating load reduction system. It reduces the thermal gap that your existing heating system must close, but it does not eliminate that gap entirely. In a Cleveland home, on a January morning when the outdoor temperature is 8 degrees, a properly installed 40-foot earth tube brings incoming air to approximately 50 degrees. Your furnace still needs to close a gap of 20 degrees to reach 70. That gap costs money. Less money than before, dramatically less money than before, but not zero money. If your expectation going into an earth tube installation is that your heating bill will disappear entirely, that expectation will not be met, and the disappointment will be disproportionate to the actual shortfall, because the system will be delivering substantial savings that feel inadequate against an unrealistic baseline. The correct expectation is a 50 to 78% reduction in heating load in northern climates, improving to 8 to 12% above that baseline by the third year of operation. On a January gas bill of $200 in a cold climate, that means an expected bill of $44 to $100 after installation, declining slightly in years 2 and 3. That is a genuine and substantial improvement. It is not zero. Managing that expectation before installation is the difference between a homeowner who is deeply satisfied with their system's performance and one who feels vaguely disappointed despite receiving exactly the documented results. The second limitation concerns soil conditions, which vary significantly across residential properties and which affect both the ease of installation and the thermal performance of the system. Rocky soil that prevents trenching to the required 4-foot depth without extraordinary effort or professional excavation equipment changes the installation economics significantly. In areas of the country where bedrock is close to the surface parts of New England, the upper Midwest, and the Appalachian region, the cost of achieving adequate burial depth may require professional excavation that pushes the total installation cost well above the sub-$500 figure that applies in areas with deep, workable soil. In these situations, the economics still favor installation over the long term, but the payback period extends from 1 to 2 winters toward 3 to 5 winters, which changes the financial calculus for households with constrained budgets or shorter planning horizons. Soil moisture content also affects thermal performance in ways that most installation guides understate. Dry, sandy soil has lower thermal conductivity than moist, clay-rich soil, which means it transfers heat less efficiently to the air moving through the pipe. In arid western climates where soil moisture is consistently low, earth tube performance may fall toward the lower end of the documented range rather than the middle or upper end. This is not a reason to avoid installation in those climates, but it is a reason to use conservative performance estimates when calculating expected savings. The Courtright Center and Bemidji Biohouse data, which represent some of the most frequently cited performance benchmarks, were collected in climates with adequate soil moisture. Extrapolating those numbers directly to an installation in the high desert of Nevada or Arizona, without adjustment for soil moisture differences, would produce optimistic estimates that the actual system might not meet. The third limitation concerns the relationship between earth tube systems and radon, which is a legitimate concern that deserves direct and careful treatment rather than dismissal. Radon is a naturally occurring radioactive gas produced by the decay of uranium in soil and rock. It is present in varying concentrations across different geological formations, and it can accumulate to harmful levels in buildings when it enters through foundation cracks, sump pits, and other pathways from the soil. The concern with earth tube systems is that they create a direct air pathway from the soil into the home's air handling system, and that pathway could potentially carry radon along with the pre-warmed air This concern is legitimate and should not be minimized. In areas of known elevated radon concentration, which include significant portions of Pennsylvania, Ohio, Iowa, Illinois, and other states, the radon implications of an earth tube installation require serious consideration. The EPA maintains maps of radon risk zones across the country, and any homeowner in a Zone 1 area where indoor radon levels above the EPA action level of 4 picocuries per liter are predicted in a significant percentage of homes should test their existing indoor radon levels before installing an earth tube system, and should consult with a radon mitigation professional about the appropriate design modifications for their specific situation. The good news is that earth tube systems in radon-affected areas are not simply contraindicated. They can be designed with radon mitigation features that address the concern without eliminating the thermal benefit. The key design modification is ensuring that the earth tube intake is positioned well away from the building foundation, that the system maintains slight positive pressure in the air handling pathway rather than drawing air through foundation penetrations, and that a radon-resistant membrane or activated carbon filter is incorporated into the intake assembly. These modifications add cost and complexity to the installation, but in most cases they do not eliminate the economic case for the system. They adjust it. The fourth limitation is temporal and concerns the interaction between earth tube systems and the longer-term evolution of the residential building stock. Earth tube systems deliver their maximum benefit in existing homes that were built with gas heating as the assumed infrastructure and that have no practical near-term pathway to complete heating electrification. For a household that is planning to replace its gas heating system with a cold climate heat pump within the next 5 years, the investment in an earth tube system needs to be evaluated against that timeline. A cold climate heat pump operating at a coefficient of performance of 3 or 4 already achieves a significant efficiency advantage over gas heating, and while an earth tube system can improve the performance of a heat pump by preconditioning the incoming ventilation air, the incremental benefit relative to the installation cost is somewhat smaller than it is for a gas heating application. This is not a reason to defer earth tube installation if you have no near-term plan to electrify your heating. For the vast majority of existing homes in the northern United States, complete heating electrification is not a near-term practical reality, whether because of the upfront cost of cold climate heat pumps, the electrical service upgrade requirements of many older homes, the supply and installation backlogs in the heat pump contractor market, or simply the financial priorities of the household. For those homes, which represent the overwhelming majority of the 74 million households on gas heating infrastructure, an earth tube system installed today begins delivering savings immediately and continues delivering them indefinitely, regardless of what heating technology eventually replaces the existing gas furnace. The fifth and perhaps most practically significant limitation for many homeowners is the yard geometry constraint. A 40-foot earth tube requires 40 feet of available yard running in a direction that permits a straight or gently curved run from an outdoor intake point to the home's air return connection. Many urban and suburban properties have yards that accommodate this requirement easily. Some do not. Corner lots, properties with utility easements crossing the yard, properties with mature trees whose root systems would be disturbed by trenching, and properties with irregularly shaped lots that prevent a straight run of adequate length all present challenges that require either creative routing, reduced tube length with correspondingly reduced performance, or in some cases acknowledgement that the property geometry makes a full performance installation impractical. Reduced tube length installations are worth understanding because they are significantly better than no installation, even if they fall short of the full performance of a 40-foot system. A 20-foot tube at 4 feet of depth in northern Ohio delivers approximately 25 to 30 degrees of passive thermal gain rather than the 40 to 45 degrees a 40-foot tube provides. The heating load reduction is proportionally smaller, perhaps 30 to 40% rather than 50 to 60, but the installation cost is correspondingly lower and the payback period remains well under 2 years. For properties where 40 feet is not achievable, 20 feet is better than 0 by a margin that is economically significant, even if it is not as dramatic as the full-length case studies suggest. None of these limitations undermines the fundamental case for earth tube systems. They refine it, they describe the conditions under which the case is strongest and the conditions under which it requires modification. They provide the honest, specific information that allows a homeowner to evaluate their particular situation accurately, rather than applying a generalized enthusiasm that may not match their specific circumstances. The physics is real, the savings are real, the suppression was real. And the path from where you are now to a January gas bill that reflects 55-degree air entering your furnace instead of 8-degree air is real, accessible, and within the capability of anyone willing to engage with the specifics honestly, including the specifics that counsel caution, because caution applied in the right places is what produces a system that performs for 30 years rather than one that creates problems in the second winter. The ground does not oversell itself. It simply holds its temperature 4 feet down and waits. We have arrived at the place in this documentary where the accumulated weight of evidence, history, economics, and practical instruction needs to be resolved into something actionable. Not in the vague motivational sense of a conclusion that tells you to believe in yourself and take charge of your energy future. In the specific, sequential, decision-by-decision sense of a person who has absorbed what this documentary has presented and needs to know what to do next, in what order, and why each step matters. The first step is assessment, and it is done before you touch a shovel or visit a hardware store or call an equipment rental outlet. Assessment means gathering the specific information about your property, your climate, and your existing heating infrastructure that determines whether your installation will fall toward the high end or the low end of the documented performance range, and whether there are site-specific factors that require design modifications before you proceed. This is not a step that requires professional engagement in most cases. It is a step that requires an afternoon of observation, measurement, and research using publicly available resources. Start with your yard geometry. Walk the perimeter of your property and identify the longest, straight, or gently curved run available from any point on the property boundary toward your home's mechanical room or the location of your air return system. Measure that distance. If it is 40 feet or more, you have the geometry for a full performance installation. If it is between 20 and 40 feet, you have the geometry for a reduced length installation that will still deliver meaningful savings. If your property geometry genuinely cannot accommodate 20 feet of run in any direction, you are in a small minority of urban properties where the installation is not practical, and knowing that before you invest further time is valuable information. Next, evaluate your soil. Dig a test hole in the area where you are considering routing the tube. Dig it to 18 inches, which is enough to assess the character of the soil you will be trenching through. Soil that comes out easily and holds its shape reasonably well is workable with a rental trencher. Soil that is predominantly gravel or that encounters rock within the first 18 inches is telling you that your trenching costs will be higher than the standard estimate and that you should adjust your economics accordingly. Soil that is consistently wet and poorly drained may indicate a high water table that warrants further investigation before committing to a buried installation. Then check your regional radon status. The EPA's radon zone map is freely available online, and your county's designation tells you whether radon is a significant concern in your area. Zone 1 counties require additional design consideration as described in the previous part of this documentary. Zone 2 and Zone 3 counties have lower radon risk, and while radon testing before and after installation is always prudent, the design modifications required for radon management are less critical in those areas. Finally, examine your existing heating system's air return configuration. Locate the cold air return, identify where it connects to the furnace, and assess the accessibility of that connection point for the modification that will integrate the earth tube supply into your existing ductwork. In most forced air systems, the cold air return has a readily accessible section in the basement or utility room where an additional inlet can be introduced without significant ductwork modification. In homes where the air return runs through finished walls or ceilings with limited access, the integration may require more planning, but it is rarely insurmountable. With the assessment complete, you have the information you need to design your specific installation. The design decisions are straightforward once the assessment data is in hand. Tube length is determined by available run distance, up to 60 feet in the coldest climates and 40 feet in most others. Tube diameter is 8 inches for most residential applications, 10 inches for homes with larger air volumes or in climates where maximum thermal gain justifies the incremental cost. Burial depth is 4 feet minimum, 5 feet in Zone 1, cold climates where additional performance and radon management both favor greater depth. Slope is 1 inch per 10 feet, continuous and verified before pipe bedding. The materials list for a standard 40-foot, 8-inch installation is short and specific. 40 feet of schedule, 40 smooth-bore PVC pipe and 8-inch diameter, available at most building supply outlets and plumbing wholesalers. Standard PVC couplings and primer and cement for joining pipe sections. A screened animal-proof intake cap and 8-inch diameter, available at HVAC supply outlets. An inline duct fan rated for 200 to 250 CFM at the static pressure of your system, available online or at HVAC supply outlets in a range of configurations. A condensate drain fitting for the intake end. A transition fitting to match the 8-inch tube to your existing ductwork dimensions at the house end. A manual or motorized damper for the house end connection. Bedding sand if your soil is rocky or inconsistent. The tools required are those found in most households, supplemented by the rental trencher. A tape measure, a long level or transit for slope verification, basic hand tools for pipe cutting and fitting, a drill and hole saw for the ductwork penetration, and sheet metal screws and HVAC tape for the duct connection. Nothing on this list requires specialized knowledge or professional licensing to operate. The rental trencher, which is the one piece of equipment that most homeowners do not own, is available at virtually every equipment rental outlet in the country and requires no special training beyond what the rental staff will explain in the 5 minutes before you drive away with it. The installation sequence matters because getting it wrong at an early stage creates problems that are expensive or impossible to correct without reopening the trench. The correct sequence is this: establish the intake location and mark the complete route of the trench before breaking any ground. Verify that no utility lines run through the trenching area by calling your utility locating service, which in the United States is reached through the 811 number and is free and mandatory before any digging. This step is not optional and is not a bureaucratic formality. Utility lines at residential properties are frequently shallower than you expect, and a trencher that contacts a buried electrical or gas line creates a situation that is dangerous, expensive, and entirely preventable. With utilities located and the route marked, cut the trench to the required depth along its full length before placing any pipe. Verify the slope at multiple points using the level. Adjust the trench bottom where necessary to achieve continuous slope from the house end to the intake end. Place bedding sand at the intake end if required by your soil conditions. Lower the pipe into the trench starting at the house end, joining sections as you go. Verify the slope again with the pipe in place before backfilling. Install the drain fitting at the intake end. Install the screened intake cap. Backfill the trench in lifts, compacting lightly as you go to prevent settling that could create low points and compromise the slope. At the house end, make the ductwork penetration, install the transition fitting, connect the inline fan in pull configuration with the fan at the house end drawing air through the tube, install the damper, and make the final connection into the cold air return. Seal all connections with HVAC tape. Test the system by running the fan and verifying airflow at the intake end with a simple tissue or piece of paper that should be drawn toward the intake cap when the fan is operating. The entire installation, from the first trench cut to the final ductwork connection, typically takes 1 full day for a homeowner working alone with a rental trencher. 2 people working together can complete it in half a day. The trencher rental period of 1 day is sufficient for most installations with time to spare. After installation, the system requires no scheduled maintenance beyond an annual inspection of the intake screen to clear any debris that may have accumulated and periodic monitoring of the fan to ensure it is operating correctly. The fan is the only component with a finite service life, and its condition is easily assessed by listening for unusual noise or measuring airflow at the intake. A fan that is beginning to fail will show reduced airflow before it stops entirely, giving adequate warning for replacement before system performance degrades. The first heating season with the system operating will show the performance improvement in your gas bills with a directness that requires no technical analysis. Your January bill will be lower than January bills in previous years, substantially lower in most northern climates. And the difference will be the clearest possible confirmation that the physics described in this documentary, validated by researchers across 8 decades and 3 continents, operates exactly as documented in the ground beneath your specific yard. By the third heating season, the system will have reached its performance plateau, and the savings it delivers will be the savings it continues to deliver for as long as the pipe remains in the ground, which, for Schedule 40 PVC in a buried residential application, is longer than the mortgage on your house. Longer in all probability than the house itself will stand in its current form. The man in Sugar Creek installed his system in 1986. He is in his 80s now. The pipe he laid with a shovel over 3 weekends because he did not want to pay for a rental machine is still in the ground. It is still warm. His January bill is still $31. He has never, in the 4 decades since he dug that first trench, written a check to the gas company for the money he would have spent if he had not known what the earth beneath his yard was willing to do for free. He knew because he was stubborn enough to find out. Because this documentary exists, the difference between knowing and acting is a trench, 4 feet deep, 40 feet long, and 1 weekend wide. The earth is holding 55 degrees right now beneath your yard as you read or listen to these words. It was holding that temperature last January when you wrote your heating bill. It will hold it next January. What happens on that January depends entirely on whether there is a pipe down there to capture what the ground has been offering you all along. Every winter, for every year you have lived in your house, whether or not you knew to ask for it,